Okay, so tomorrow, it's always been the tradition on the day before Thanksgiving that it's just become known as Africa Day. So we'll show you footage of me 30 years ago. And let's get this straight right now. I was thinner, but my glasses were bigger. So my glasses have gotten smaller, my waist has gotten bigger. That's kind of the ratio. So the other tradition is that I always make ranch eggs. And if you guys want to bring anything else to have with it, that's fine. So I just need,
Bagels.
huh?
Bagels. Hopefully we don't burn it this time.
Bagels and
Yeah,
eggs.
if somebody wants to bring something else. So what I need is I just need, besides Louis, because Louis has already contributed a dozen eggs. So I need one person to bring a dozen eggs.
I got you.
You got it?
Yeah.
Don't forget,
I won't.
or we're not gonna have ranch eggs,
He'll bring a lot more than a dozen.
okay? I just need 1 dozen.
Can I bring
Don't
like
dummy snakes and be like, dang, I forgot.
Can I bring can I bring like a grill top thing and plug it into the wall and start making bacon?
Yeah, I've got
No, this man's a
griddle.
cook. This man, I will vouch for this man. He
If
gives,
you wanna bring your own, I've also got a griddle, if you wanna do that.
Make some pancakes too, Connor.
I want to bring some ribs.
No, no. No, I can't have barbecue, because, no.
you like barbecue?
I'm such a
used
good
to love
barbecue cook.
barbecue, but now if I eat barbecue, I am miserable for days with heartburn.
Well, you'll have your Thanksgiving break to get over.
No, nope, I don't want to be miserable during that time.
And then we'll give you another one. On
So you
Monday.
feel bad after Thanksgiving, or how
Huh?
you feeling after?
No,
Thanksgiving?
that's why I don't eat barbecue.
Oh,
So,
Is it just like the
Just the
sauce?
barbecue.
yeah, and it's just weird, like, even if I just smell it, it's at the point now if I just smell it, and it sucks.
It's
because
just acidic.
I used to love barbecue, and now if I eat it, oh, shacks me up. Okay.
I kind of want to bring.
All right, so let's talk physics. So let's talk about number 4, because if your answer to 4A is wrong, everything else is going to be wrong.
Yes, please, I'm scared.
So that answer to 4A on that spring constant should be around your age,
Should have both.
okay?
Is that, I'm making an egg.
That's an ish, but pretty close. Should be a little bit more. What do you have? What do you have?
No,
Okay.
I go home.
All right. Now, here's what you want to keep in mind. What you're plotting on this graph is not the length of the spring, but the elongation of the spring. You're going to put force here, and you're going to put elongation here. And obeying Hooke's law, you're assuming that it's going to be a linear function. So here's what commonly gets jacked up with this. You have F equals Kx. So this is what makes it a linear function. This is just y equals mx, okay?
Plus.
So force is a linear function of your displacement. So if I want to stretch a spring twice as far, that means I'm going to exert twice as much force. Okay? Cool with that.
Yeah.
So this K is your spring constant. But when you look at energy, which is us, let's talk about us. So that's 1/2 K x squared. So this is the slope, right? So in terms of energy, if you double the amount of stretch, then your energy goes up by a factor of 4. So us is 1/2 kx squared. Force is kx, okay? So keep those two things straight. All right, so when you get to question number 6, okay? So box of crayons, fricks on the surface, hits the spring, how much kinetic energy does the box have? So here's the deal. So what you want to do on number 6, what I would recommend very, very highly, is that you start off and you're going to have, I'm going to have some kinetic energy, I'm going to have some us, and I'm going to have a sum, okay? So what I would recommend is at the beginning of number 4, you know the mass and you know the velocity of that box of crayons. So knowing that, you can find that pure kinetic energy, meaning that's 1/2 mv squared. So I would start off and say, okay, here I am just moving. That's all kinetic energy. I've stored nothing as us, so that's OJ, and then you're going to have that sum. So what you should see on number 6, that sum is 2 joules. So when that box of crayons is moving as a pure form of energy, it has 2 joules of kinetic energy. So that means afterwards, the sum of all of those energies has to add up to 2. Because if that initial kinetic energy calculation is wrong, everything else is going to be wrong. So when you get to 6A, how much kinetic energy does the box have if the spring is compressed by 2 centimeters? So you can figure out us, because that's going to be 1/2 kx squared. You know how far it gets compressed, only 2 centimeters, is about like yay. Make sure you convert that into meters. So you can figure out how much of that energy is stored as the spring, and the balance of whatever is left over is kinetic. So obviously your kinetic energy on A has to be less than 2 joules, okay? Because you haven't compressed that spring very far, okay? Your answer to 6B would make a pretty decent GPA, okay? Not bad. Now again, obviously, what does your answer to 6B have to be less than?
4.
4. Because it was initially at all kinetic energy is moving at 4 meters per second. So if you've lost some of that energy to the spring, it has to be going less than 4 meters per second. And then on C, when you find that maximum compression, it's all of that energy is then stored as us. Solve for X. Okay? And if you're in centimeters, it should be between 5 and 10 centimeters. Okay. On number 7, it's the same idea. You're going to compress them against the spring. You're going to release it with what velocity does Jerry have when he takes off from the spring. So it's kind of like this. You're going to compress the spring. It's all going to be stored as potential energy as us. You're going to let go. It's the same idea as like you pull back a bow and arrow, whatever. Same idea. Mother Nature likes kinetic energy more than she likes potential energy. So when you let go of that spring is going to expand and it's going to push Jerry and the mouse away. So that velocity on 7A should be a just okay GPA. Okay, not stellar, just okay. And then on 7B, here's what's happening on that one. So on 7B, here's number 7 in its entirety. So you're going to compress this spring. So here's a little skateboard. There's Jerry the mouse. Okay? They're sitting there. It's all about us at that point. Okay? It's all us. Boom, we let go. Doink. Then it becomes all kinetic energy. Okay? Then he's going to go up the half pipe, and then it's all going to be UG. So the potential energy that you store in the spring becomes kinetic energy as he's moving along. Becomes kinetic energy as he's moving along, which becomes UG at the top. So it's basically all the same thing. Us becomes KT, becomes UG. Okay? So that height on 7B should be around 1/2 meter. It's an ish, but it's something around there. Now, on number 8, here's your setup. Or a rubber band. see if rubber bands aren't old and brittle. Okay. So we kind of visual of what's happening on number 8. So you're standing up here on top of the bridge, and here's your bungee cord, right? So you're going to fall for a certain amount of distance before the bungee cord begins to stretch. Then, as it stretches, it's going to go like this, right? So what you're going to find out first is, okay, how fast is kid moving just when he hits the end of the bungee cord? So that's just old school kinematic equations, okay? It's old school. Now, the trick is going to be, so he falls, and then bam, okay? So this thing stretches out. So at the bottom of that elongation, you are 31 meters below the bridge. So what you want to do is realize the energy that you store in stretching that rubber band is equal to the energy the potential energy that you had at the top. So the UG here is going to equal the total amount of energy that you have when you stretch the cord, okay? So you're here, you fall, you end up 31 meters below the bridge. So you go, the UG that you store using MGH is equal to the kinetic energy or the energy that you store in that spring, which is going to be 1/2 kx squared. Your H is 31, because that's how far you are below the bridge. Your X is how far the bungee cord itself stretches, okay? That's how much energy that you're going to store there. So if all goes well, that bungee cord constant on B should be around 100 newtons per meter, okay? A little bit above, but something around in there. Now, here's the whole idea when you get to the dynamics of the forces. So if you're going to stop, and this is going to be important when you look at the lab today, okay, with springs, it's the same idea. So as that spring begins to stretch, as it stretches, what happens to the amount of downward force created by gravity as the spring stretches? What happens to that downward force?
It's the same.
It's the exact same. That doesn't matter. It's not going to change. Because that's just mg, right? But as it stretches, what happens to the upward force created by the bungee cord?
Increase.
That increases because F equals kx. So the farther you stretch that spring, the more that upward force increases. Okay? Now, if you're going to stop this from going down, what do you know about the upward force on the bungee cord relative to the downward force of gravity?
It's to be the same or greater.
Yeah, because if the upward force of the bungee cord never becomes greater than the downward pull of gravity, you're never going to stop. Okay? It's not going to happen. So you want to. So at some point, if you're going to stop, that upward force of the bungee cord has to be bigger than the downward force of gravity. Okay? So when you get to E, when you find that acceleration, remember that force net is going to be the difference between the force from the bungee cord and your gravitational force. That's the net force, okay? And that net force also equals mass times acceleration. And the force from the bungee cord is going to be kx. At that point, you're going to know the spring constant. You're going to know how far it stretches, okay? You're going to know the mass, you know the gravitational acceleration, solve for A. So if all goes well on 8E, that should be something around the legal drinking age, okay?
18.
16
In the
you're
United
up.
States, and not when your parents are out of town, okay? The legal drinking age. All right, now let's talk about number 9.
I've been doing since 15 with my
There's two ways that you can work number 9, okay? One option on number 9 is what's going to be the speed of impact, okay? So one option is that you're gonna shoot this thing at a 45-degree angle. So one option is that you go old school. You find your Vx, you find your Vy initial. You use that Vy initial to find your maximum height. Then you know how far it's gonna fall. So you use that equation to find your maximum height. Then you use that equation to find your vertical component at impact. You're still going to know the same Vx. Find the resultant of those two, there's your speed. Okay? That's an option. It's complicated, but if you like projectile motion and using that equation, there you go. Okay? And then you end up using the Pythagorean theorem because you know Vx squared, your final Vy, square that, find the hypotenuse. You don't have to have the angle. All you're asked to find is the speed. Now, if you look at this, you've launched this thing at 185 meters per second. So when it lands, what do you know about the speed? It's got to be bigger or smaller than 185?
Bigger.
Bigger, because it's falling all the way down to the ground. Okay? So that's one way you can do it. If you like that, if you have a comfort zone of projectile motion in that equation, that's in your wheelhouse. It's gravy. Now, what's the other way you can work the problem?
Using potential.
Energy. Okay, let's talk about energy. So, from an energy perspective, when it's launched, what types of energy does it have? Again,
Potential.
some amount of initial kinetic energy. Right? Does this kinetic energy depend upon the angle of launch?
No.
Why?
Because it's just velocity.
It's a scalar quantity. Okay, it's just a launch. I don't care if I launch that thing at a 45-degree angle. If I launch it horizontally, I throw it straight down, I throw it straight up. I have no way to plug that into my kinetic energy equation as long as I shoot it at 185 meters per second. The direction in which I launch that thing does not matter. Okay? Will it impact my height? Yeah, it will. Will it impact my Vx when it lands? Yeah. But it's not going to change my kinetic energy. When it lands, what's the only type of energy it's going to have? Kinetic. So you can go, UG plus KT naught equals my final kinetic energy. True?
True.
So how are you going to calculate UG?
MGH.
How are you going to calculate your initial kinetic energy?
Half mv squared.
1/2 mv naught squared. And that all together adds up to
KT prime.
1/2 m
VC squared.
v squared. What happens to your masses?
Cancel.
Why didn't I give you the mass?
Because they're not needed.
Doesn't matter. Because you multiply everything by 2 to get rid of those annoying fractions.
Yes.
2gh plus v naught squared equals, otherwise known as
That equation.
Equation.
that equation. I don't care how you do it. You can either just, from an energy perspective, or you can work it on a projectile motion. Obviously, which one's going to be easier?
Energy. So does it matter what height you choose?
Oh,
You just-
vastly.
But you just have to have the right V naught at that height.
Yeah.
Right, okay.
Yeah.
Wait,
Okay.
So would the velocity matter? Would the velocity sign matter then?
Huh?
Because what if you did it on the way down?
Matter.
It would. Oh yeah, I guess.
Because it's squared.
Yeah,
Because it's squared.
that makes sense.
Okay. All right. Anything else? The problems from the book are pretty straightforward, pretty easy. Going once, going twice. So we should be back
We'll be
tomorrow.
back tomorrow.
I feel like he's home.
What do you want?
Okay, so
I bet he is.
this lab is going to combine a whole bunch of different things. Okay, I'd like it first off as it goes old school.
You're out of here.
So the first thing that you need to
It won't
do
matter.
is to establish the spring constant. Okay? So you're going to hang different masses from there. You're going to draw a line of, listen to me, you're going to draw a line of best fit, you are going to circle the points that are on that graph, that are on that line of best fit, and you are going to show me how you calculated the spring constant. Because if that's wrong, everything is going to be wrong, okay? And typically for these springs, that's usually around 60 to 80, okay? As far as what that numeric value goes. So, you can have your force, you can have your elongation, some points, boom, draw
Right,
that
so-
straight line,
Is the constant in joules then?
because it's newtons per meter, not newton meters.
Oh, okay.
Yeah, big difference. Okay, so that's the first thing you're gonna do. Now, down below, there's a diagram, okay? And you're gonna have 3 different rings.
3 rings.
The diagram actually has you putting a hook at the top. Don't do that. You wanna put a hook at, a ring at the top with a rod, so that way you can adjust the position of this so that that spring is in the exact middle of the rings. So this first ring, set the bottom of that ring level with the bottom of the unstretched spring, which sounds like something out of a Dr. Seuss book. So at the bottom of the ring, at the bottom of the unstretched spring, which is tough to say. So that's going to be right here. So you can use that. So let's say, for example, you take that 500 gram mass and you hook that onto it. Then you can use that as a reference to measure how far it stretches. Remember, you are plotting elongation. You are not plotting length, okay? So you want to measure how far it moves from that equilibrium point. So you're going to add the different weights. Oddly enough, it's going to stretch further and further and further. Boom, there you go. Now, once you get done with that, then we're going to make this thing begin to oscillate. So is this, you're going to hook up a 1 kilogram mass. So over here on
Ooh, it's awesome.
page 2, you're going to do this with a 1 kilogram mass and then a 1.2 kilogram mass. So on the 1.2, so I'm going to hook this up like this. And you got this action going.
See that thing
That's a
awesome.
lot of action.
That's a
See
lot of
that?
action.
Okay.
So you're going to have these rings up here like this.
What?
You're going to have some other rings down here.
Oh, there's a bunch of other.
Yeah, why so many rings?
You'll see. So this is your equilibrium position. Okay? So then you're going to make it oscillate like this.
Well,
Now, as it oscillates, there's 3 types of energy that are involved in that oscillation. What's one of them? Kinetic. Why do you have kinetic energy? Because you have a velocity. Now, do you think the kinetic energy value changes?
yes,
Why?
because it slows down and speeds back up.
Yeah, the velocity is changing. You're changing direction, right? So does the kinetic energy ever go to 0?
Yeah.
When?
At highest point and lowest point.
Because you're stopping to change directions, right? So if you have the maximum, if you have your minimum kinetic energy at the bottom, and your minimum kinetic energy at the top, when do you think you have your maximum kinetic energy?
In the middle.
Oh, in the middle, right? So it starts up at the, if you look at the oscillation from the top, okay? Up at the top, you have no velocity, right? Starting to fall. It's going to fall, it's going to speed up through the midpoint, then what's it going to do?
Slow down.
Then it's going to start to slow down. Then it's going to go to, and then it's going to,
Speed up.
and then it's going to
Slow down.
stop again, right? So do you think my kinetic energy is ever constant?
No,
No, why?
because the velocity is constantly changing.
Yeah, I never have constant velocity, therefore I never have constant kinetic energy. Okay? Kinetic energy is always changing. What's another type of energy that I'm going to have?
Potential.
What kind?
Ugh.
I'm going to have UG. Why am I going to have UG?
Because it's above the ground.
Yeah, so I have a certain value of MGH, right? So as this thing is oscillating, is my UGG value changing?
Yeah.
Yes,
Why?
because its height is
It's
changing.
getting
My
higher.
height is changing, right? Now, within this oscillation, okay, within this oscillation, when does it have its maximum UGG?
Top.
At the top, why?
Highest.
Height.
That's at its highest point. That's when it has its maximum value of H, right? When does it have its minimum UGG?
At the
Bottom.
Bottom. Okay? So that's two. We have kinetic energy and we have UGG. What's the third type of energy?
Us.
Us. Now, why don't I do this lab with like a string?
Because it
It
wouldn't
doesn't
stretch.
stretch.
There's no
Yeah,
house.
we'd be like, that's boring.
Yeah.
Snap.
Snap, boom, there you go. That was fun. Wow. Physics, yay. Right? So, why do we use springs? What are springs capable of storing?
Potential.
Potential energy. You can store us, right?
Right.
Now, is us changing as it oscillates?
Yes.
Why is us changing as it
Elongation's
oscillates?
changing.
You're changing the elongation. Now, when do you have your maximum elongation?
Bottom.
So when do you store your maximum us?
Bottom.
So here's the dichotomy.
That makes sense.
You have your maximum us at the bottom, but you have your minimum at the top. You have your maximum, but your minimum
Us.
us. Got that?
Yeah.
Cool with that. Okay. So if you were to draw a graph of time versus, say, kinetic energy, and let's say you were to start at the top. Here you are at the top. You're going to let it fall. We're just going to talk about kinetic energy. What would that graph look like? You're going to start at the top. It's
Sine
Starts at
wave.
0.
Just be a
going to
sine
start
wave.
at 0.
Yep.
Then what?
Go up.
Going to go up.
Come back down to 0.
Then it's going to come back down.
And then go back up.
So where is it at that
Sideways.
first 0?
When it's at the very bottom.
So at the very bottom, right? Because that's when the velocity goes to
0.
Now, it's at the bottom. So is that graph going to cross through 0 then?
No.
No.
Why not?
Because V is squared.
Because it's a scalar quantity. So what's it going to do?
Go back up.
It's going to go back up.
Sideways.
So then, where's it going to be there?
Zero.
Top.
Oh.
At the top, right? Because that's when that kinetic energy goes back to 0.
Yep.
Okay? So that's my kinetic energy graph. What would my us graph look like if I were to overlay it on that same idea? So what would
It would
us?
be a,
So again, I'm starting up at the top.
it'd be a
It's gonna
cosine
start
wave.
like a little, not at 0, but a little
Why
up.
wouldn't it start at 0?
Because it's still elongated.
Yeah, it's still elongated, right?
Yeah.
The only way it could start at 0 is if I had that all the way up at the top.
Yeah.
Okay? But I still got some us. So up at the top, is my us at least going to be a relative minimum or a relative maximum?
Minimum.
Relative minimum. It's not going to be 0, right? So it might start, say, something like this.
Yeah.
Okay?
Okay.
Then it's going to fall, right?
Yeah.
So what's that graph going to do? So as that mass falls, what's going to happen to the amount of us it's going to store?
It's gonna
It'd
go up.
It's
increase.
going to go up. Now, when is my us going to be in maximum?
At the very
Bottom.
bottom.
At the bottom. So this is going to go something like, so at the bottom, that's my us is going to be at
Maximum.
Maximum.
its biggest value. At the top is when it's going to be,
And it's the lowest.
Minimum.
so are the graphs going to look exactly identical?
No.
No. Now, what would the graph of, let's go green,
Somebody's phone is buzzing.
UGG
Probably
look like?
mine. Sorry.
Just flip it upside down.
So UGG is going to be at the biggest value at
The top.
the top, okay? And it's going to be at a minimum value when it's at
The bottom.
the bottom. So it's going to go something like that. True?
Yeah.
Yeah.
Now, another thing would happen. If you neglect friction, At any point, if you added all those energies together, what would you get?
You get the total amount of energy in the system.
Fantastic. You would get the total amount of energy in the system, because all you're doing is
Finding the
how it's changing forms, right?
Yeah.
Okay?
Good job, Lou.
But at any given point, they would all add up to the same thing, right? Now, if I do this, obviously after a period of time, what's it going to do?
Stop.
It's going to stop. Where did the energy go?
Friction. Heat.
Friction, heat, right? So anytime you make those particles stretch and compress, stretch and compress, that's going to generate some heat. Now, it isn't like, ooh, the room is cold. Oh, make a spring oscillate. That'll warm up the room, okay? And it isn't like, hot, okay? No, okay? But there is a little bit of thermal energy that's being created. There's some air resistance, right? Okay, there's some air resistance. So as it moves through the air, you're gonna lose some energy there. You're gonna lose some energy in making the atoms vibrate. Okay, so thermal energy is the great dissipator. Okay, just like if I set up a pendulum and let it swing back and forth, eventually what's that pendulum going to do?
Stop.
It's going to settle at the bottom, lowest possible energy state. Got that idea?
No.
Okay. So in terms of data, so you're going to put a 1.2 kilogram mass, okay? You're going to pull it down and you're going to begin to have it oscillate. Once it's oscillating, then you set the bottom two rings. Don't touch the top ring. You're only going to adjust the bottom two rings. So you're going to have the bottom ring, which is tough to do, okay? Oddly enough, at the bottom of the oscillation. And then you're going to have the top ring at the top of the oscillation, okay? So this right here represents, later on we'll talk more about this, this is called the amplitude of the oscillation, okay? So here's what you need. So pay particular attention to this diagram on the front, because you have three different diagrams. So X1 is going to be from the bottom ring to the top, because this goes something back to Pop's say. Even though it's oscillating, at the top of the ring, it still has some us because of the fact that it's still stretched, okay? So when this is going to represent this X1, okay? From here to here. So this is going to be your X1. Now,
Why you get your own out?
X2 is going to be from the ring to the bottom. So your X's, okay, are a measure of us. So here's that unstretched length. So if you stretch it to X1, that's a certain amount of energy. You stretch it to X2, that's more energy because you're stretching it a further difference. So the change in us is going to be the difference in those energies. Okay? So over here on page 2, you're going to measure X1. You're going to measure X2. Now, H is going to be the difference between those two. So our value of H is going to be the height change that you get from the bottom of the oscillation to the top of the oscillation. So if you screw this up, it's because you don't pay attention to what you're measuring. This is going to be X1. This is going to be X2. That's going to be your height.
So your height is your amplitude?
Yes.
Okay.
Because that's how much that gravitational potential energy is changing within that system.
Gotcha.
Okay. Now, you can do that for trial 1, okay? It's kind of a small oscillation. Trial 2 is going to be the same setup, but it's going to be a bigger oscillation. The third trial is that you're going to take off the 200 gram mass and you're going to put on a 1.5 kilogram mass. Okay? So, 2 trials with the 1.2, one with the small oscillation, one with the bigger oscillation. Okay, this is why you have to have these rings so you can adjust that position, so it's oscillating right there in the middle, okay? And again, don't do this. Don't lift this up and then set the ring. You have to let it oscillate and then you set your rings, okay? Get it oscillating, then set the rings. Now, listen to me. Listen to me very carefully. Down below, I want you to show the calculations for trial 1 in the space below. I don't have to see all of them, but I do want to see these calculations, okay? Show me, and writing down the formula is not showing me the calculations, okay? Putting in the numbers, that with the units is showing me the calculations, okay? So like on this is how you're going to calculate us. And so I even tell you, the only ones I really have to see are for trial 1. If you want to show me the other ones, that's cool. But at a minimum, down here, where I've got this space, okay, here, this is where I want to see those calculations. Down here, trial 1. You're going to put the numbers up here, the values that you get, but the actual calculations for trial 1 are going to go down here. Anybody should be able to take your paper and say, hey, how did you calculate U1? How did you calculate U2? How did you calculate delta us? How did you calculate other? Okay? All right, so focus on getting the data. You don't even have to have that line, the slope of the line calculated to get the data for the oscillations. Make sure that you clamp this thing down, okay? Or otherwise it's going to go doink, and bad things are going to happen. So make sure that you clamp this down. Okay, let's go do science.
What is U1 and U2?
U1 is the potential energy.
Okay.
U2 is the energy from here to here.